So this is going towards all pentane. So if you put in 75% pentane, you end up with all pentane. If you put in 25% pentane, you end up with all dichloromethane. Okay? So what do you think the residue curve for this looks like? If you wanted to transfer this now into one dimension, nodes, simple nodes, and lines with arrows. Can you transfer it? Go ahead.
You have an unstable node in the middle.
You have an unstable node where? In the middle is correct.
At the azeotrope.
At the azeotrope. So the azeotrope is an unstable node, and
Each stream is a stable node.
each node, each. So here is pure dichloromethane, and here is pure pentane. They're both stable nodes. Does that make sense? So if you're above the azeotrope, you're going to end up, but this is why azeotropes are a problem, of course. It's because if you put in any composition here, what are the two components you can make by distillation? You can make the azeotrope and dichloromethane. You can't get pure pentane. If you're here, you can make pure pentane in the azeotrope, and you can't make pure dichloromethane. You can't make pure dichloromethane. You can only make pentane in the azeotrope. Does that make sense? So this is why it's a barrier to distillation. So at the moment, when we just have a two-component system, you can't make two pure streams with a distillation column in this system. I'm losing people. I got an exam coming mid-year. This is too much. But we'll, what's happening to temperature along these lines? Which is the lowest temperature? Say it loud, that's right.
Unstable node.
The unstable node is the lowest temperature in the system. It has a temperature of 30.6 degrees C. And does it increase towards both the stable nodes? Okay. So this is 34.9 degrees C, that's the pentane boiling point. And the dichloromethane boiling point is 38.9 degrees C. So even though this is the heavy, and this is the light, the azeotrope is lighter. Yes?
Why is that?
Why is that? That's what thermo was supposed to teach you, remember?
Did he just take his
Remember that?
Yeah.
Okay? There's the high boiler, there's dichloromethane, there's pentane, and there's the minimum boiling azeotrope. We will get to maximum boiling azeotropes. These are simpler, okay? You're a little more used to these because maybe you've done an experiment with ethanol water at some point in your past. You can imagine ethanol water which has a minimum boiling azeotrope. Most azeotropes are minimum boilers, but there are maximum boilers. Which way around is it? Minimum boilers. It means that they dislike being mixed is the simplest answer. Okay, it's your answer like molecularly, but it's obviously more complicated than that. But basically, they'd rather be pure components than be the mixture makes them more volatile. So the presence of the other species makes them want to be in the vapor phase more. Is the qualitative, that's not numerical, but that's basically what's happening. And the maximum boiler is the opposite. They like being in a mixture more than they like being a pure component. Okay? And then anything that follows Ralph's law, a simple Ralph's law, is that the presence of the other component doesn't affect. They don't affect each other. So in other words, there's no activity. And this is where you need an activity coefficient, obviously, in order to adjust this. Does that ring a little bit of a bell now? Okay, you probably spent lots of time talking about it. Never thought about it in practicality. So now if you're actually trying to separate dichloromethane and pentane, you can't separate it because of that azeotrope. Okay, and that's why. So this is now what we're going to talk about, separations is, now how do you make pure pentane and dichloromethane? Okay, That's what we're going to do. Okay, so temperature increases along azeotrope, along residue curves. Okay, how am I doing? A little bit of time. Let's begin to talk about ternary mixtures. Let's start like I did here with, instead of going with an azeotrope, let's just start with a simple one. Let's do methanol, like we did in ternary. Methanol, ethanol, and propanol. Okay. Again, we can integrate the same equation as before, that the change in composition as a function of work time goes as the difference between the liquid and vapor phase. And that allows us to produce a residue curve. Again, now we're going to just draw it in a triangle diagram. And like I said before, I'm going to try to keep this notation, but it won't always be the case. We put the light here. The intermediate here, and the heavy over here. With all of these, it's important to know the boiling point. N-propanol boils at 97.2 degrees C. Methanol is at 64.5 degrees C. And ethanol is 78.2 degrees C. Now, these are that strange. These are all, probably have some of these at home. Maybe not have N-propanol, but you have isopropanol, which is similar. Okay. Okay, so before I get, let's just think about this. All right. So before I start doing, this is going to be a technique we're going to use for doing all of these. But let's just think about the binary pairs. Now, there's no azeotropes anywhere in the system. Okay. Let's just think about a binary mixture. Let's take the two easiest ones: methanol and ethanol. Which way, so in other words, we're just going to look at that one line. We're just going to do, there's no N-propanol in the system at the moment. We're just going to do a binary distillation or a simple still with ethanol, methanol in it. Which way does the residue curve go? Up or down? You can kind of look at it here for a hint. What does temperature do along the residue curve? So which way does it go in this case? Up or down? No? Which way is it going? Up. Now, this is not going to stand. Just bear with me for a second. Which is the unstable and stable node of that pair? Just in binary, okay? We're going to introduce something new in about 20 seconds, but which is the unstable and stable node? If you just had a binary pair of ethanol and methanol. Yeah, go ahead.
Methanol would be the unstable node and ethanol would be the stable node.
Put these in lightly, because one of them is going to change, okay? But for this binary pair, that's the stable node, and that's the unstable node. Let's do another easy one. Methanol and N-propanol. Is it moving to the right or to the left? Say it loud. Left. Because temperature is increasing, okay? Stop that button. Which is the unstable, which is the stable? Go ahead, Sid.
N-propanol is the stable.
Yep, and obviously methanol is the unstable. Okay? Now this is where things get a little interesting. What happens with a mixture of ethanol and propanol? Binary mixture of methanol and propanol. It goes, say it loud, go raise your hand and say it loud. Down, yes. Which is the stable, which is the unstable? Don't look, just do it without thinking about what's happened before, okay? Because I told you I'm gonna revise this a little bit. In that binary mixture, which is the stable? Yes.
The stable's propanol.
Yes, the stable is N-propanol. What's the unstable? What's it? Ethanol. Okay, so you can see where the problem is, right? What is ethanol in this ternary system? In one binary case it's an unstable, in another binary case it's a stable. Okay. So let's just, you have to kind of bear, let's see, how do we do this? You have to imagine this a little bit. Imagine you're still, again, and you're going to mix all three of these. Right now, all I've done is mix two of them. Okay, now we're going to mix all three. And I'm going to heat it and see what happens. If I have all three of them and I'm near N-propanol, what's going to end up in that still at long times? N-propanol. But if I'm here and then I have more methanol than ethanol, where am I going to end up at long times? N-propanol. If I have a mixture that's mostly methanol, but also has some ethanol and some N-propanol, where's it going to at long times? Say it loud. N-propanol. So in some way, it's heading in that direction. Okay? If I have a mixture up here that's got mostly ethanol, but it has N-propanol, methanol in it, where's it heading in long times? N-propanol. Okay. Everything seems to be heading towards N-propanol. What happens if I am right close to this edge, really close up here? Where do you think I'm going to head? N-propanol. But where am I going in the way? Going up to ethanol. Your fingernails weren't caught on that. Okay. Okay. So you don't have to, you just don't make them turn corners, okay? So if I now hook these all up. Don't cross. Okay, that's more than you need to draw to get the idea. Ethanol is neither a stable or unstable node, is it? It looks a little bit like something else that we had in ternary. Anyway, I'll tell you what it's called. It's called a saddle point. And a little bit in the book, I'm going to try to keep this convention a little more because I like it. I'm going to use an open square for a saddle point. In other words, it acts a little bit like an unstable and a little bit like a stable node. Okay? Now, we've done distillation of systems like this. So we can actually figure out some more rules, which I usually don't get to later, but I want you to think about this for a second. I want to put a mixture of methanol, ethanol, and propanol into a distillation column, because we just did it, so I want to, like, while it's fresh. What are my choice of products? What are my choice of products in a simple column? Don't worry about stills now. I'm just talking about a simple column, a simple one feed, two outlet column. That's all you've done, okay? You don't know any other kind. Yes?
Either just methanol or just N-propanol.
Okay, and so if you had to pick, what kind of things can you get from distillation? What are they called on this diagram? They're always, you said N-propanol.
Oh, yeah.
So, and then where did the methanol come out? If you want to make methanol, it comes out the distillate, top, yes. If the N-propanol is a product, where does it come out? The bottoms. So if you wanted to, what products are your basic choices in any ternary system? Your unstable and your stable nodes. If you want to make a stable node, where's it going to come out? The bottom. If you want to produce your light component, your unstable node, where's it going to come out? This. Can I make ethanol in, I'll get to you in just 1 second, okay? Can I make ethanol in a simple column? How can we make ethanol? Can't make ethanol. So can you make make stable nodes in simple columns? Sorry, can you make saddle points? Scratch what I just said. Can you make saddle points in simple columns? Nope, can't. Question?
Since temperature is always increasing along the residence line, won't your unstable always be your lightest and your stable always be your heaviest?
Yes,
Okay, just checking.
yes, yes. When we get to azeotropic, it gets a little more tricky than that, okay? But in these systems with no azeotropes, absolutely. Okay? In most cases, even with azeotropes, that's true. Okay? So, but just be careful, is my answer. If there's no azeotropes, that's true. Got it? I'm keeping to the simple for now, okay? Okay, so let me just give you some properties of reservoirs. So this is our first two-dimensional ternary residue curves. We're going to generate lots of these. Okay? And they're going to help us figure out how to design azeotropic systems. Notice the warp time disappeared. Okay? We move with warp time along the residue curve. Okay, so this is moving along with warp time, but it basically disappears. And I'll explain this. It's actually a lot easier than you think. Okay. So at any point, the residue curve is tangent to the BLE tie line. Okay, that sounds really complicated, but do you remember that this is the liquid phase composition diagram of this ternary system? Do you remember there's a vapor on top of it? What it means is, if you take any one of these points, and this is some X composition, it means that there's a vapor composition here, such that if you connect those two lines, the slope of the residue curve and that line are tangent. What does that mean? That sounds complicated, but it has an advantage. It means that if you take a system, all these mixtures, and put them in a still, and you measure the composition of the vapor and the liquid, and plot them, and draw them as vectors, you'll see some of these plots in the book. You can now draw the residue curves. You just take these little lines and connect them, and they make the residue curve. Okay? It just means that there's always a vapor. Wait, I've done it the wrong way. Sorry, that's backwards. Let me show you. Because the vapor is going to be enriched in methanol, not the other way around. Okay? I actually don't know exactly where it is, but that's wrong. Okay? I'm not sure where Y is, but the point is, there's always a vapor that's in equilibrium with that liquid, and it's going to be tangent to that residue curve. Okay? That's all it means. They don't cross. Boiling temperature increases along curves. Steady state solutions what does that mean? D something d xi is equal to 0 occur at pure components and azeotropes. When all you see is that one, it seems sort of silly. But what it means is, if you put any composition inside this triangle into a still, what do you end up with? any composition inside this triangle, what do you end up with at long warped times? N-propanol, except for two. What are the two things? If I start with a still, yeah, if I start with pure methanol, it stays pure methanol. If I start with pure ethanol, it stays pure ethanol. Obviously, but this isn't supposed to be that difficult, okay? This is an example so you get it, okay? But notice, anywhere you start, if you have any mixture, over warp time, you're going to end up in N-propanol. In other words, these aren't steady-state solutions. You can't put that composition to a still, put heat in it, and expect to stay at that composition, obviously, okay? You're only going to get steady states, you're only going to get stable, steady-state solutions are stable, unstable nodes, and saddle points. And residue curves are tangent to a common direction. Number 5 is steady-state solutions. Steady-state solutions are stable, unstable nodes, and saddle points. In other words, the three things that I just drew, they're the possibilities. Okay? And we'll find that everything's either a saddle point, a stable node, or an unstable node. So this fact that they're always tangent to each other, notice how they're all tangent to each other here. You see how all the lines are tangent to a point? They're tangent to each other. So if you know the directions of the edges, it can help you figure out how to draw them. We'll get to that. I think, so, okay, I'll let you finish that. I'll just introduce where I'm going to go next. I won't, that's the end of the notes for today. So what I'm going to teach you next is how to sketch these. And what I mean by sketching is that they won't be exact. But it's possible because of the topology of the way these work. Notice how I could draw this for the system. Now if you actually put in and measure the residue curves for methanol, ethanol, and propanol, it would not look exactly like that. But it basically looks like this. You'd still find out that's a saddle point, that's a stable node, that's an unstable node, no matter what. So the question is, what's the topology of any system? Once we add azeotropes and entrainers to the system, what that allows us to do is see where the problems are. Which systems, which are feasible entrainers, which are non-feasible entrainers. When you're going to design the column, how are you going to design it? So understanding which is going to help us to do that. So you don't actually have to know the exact shape, we can do by experimentation, but this kind of sketching, and what I wanted to get at, just give me 30 seconds, is the sketching of this is the kind of fun puzzles, and the nice thing is, the difference from doing the stuff we did before, where you actually step the stages and the composition stages, we're not going to get to any level, that level of detail. All we're going to do is this entrainer, does it work? And what kind of system can we build? Basically, we're just answering the feasibility question. So it's one step more removed in design, but it's still very useful, and hopefully you'll find it interesting. That's where we're going next. Okay? Thank you.